Good day. We are Group 5. My name is Jason Ngo,
My name is Sebastian Chenglai.
And my name is Edric Yao.
and today we are going to discuss the applications of vapor pressure in differential equations. Vapor pressure is an important element in liquids as it is the measure of tendency for the liquid to change into a gaseous state or a vapor state. Vapor pressure is directly proportional to the temperature of the liquid and it determines what state of the liquid will behave in. It also affects the humidity of the air or the amount of vapor, water vapor present in the air. As vapor pressure increases, the relative humidity increases too. This topic has many applications in the pharmaceutical industry, wherein the creation of tablets and medicine uses this concept to treat people. Pharmaceutical coating involves the use of heated air to facilitate the evaporation of solvent, which involves the use of vapor pressure to control the humidity.
So now I will be discussing about the equation we will be using. So the Clausius-Clapeyron equation is derived using thermodynamics principles. L being the latent heat of evaporation, V sub V being the vapor phase's real volumes at temperature T, V sub L being the liquid phase's real volume at temperature T the temperature, and P is the pressure. Note that the V sub V is much greater than the V sub L, so that is a good approximation. So in turn, V sub L can be cancelled out, giving us this next equation. From this, the ideal gas law is then applied to the equation above, where R is the universal gas constant. So after that, integrating both sides using variable separable, we are able to get this specific equation. Ln P is equals to negative L over RT plus Ln of C. Finally, after integrating it again, we are given our final equation. P equals C times E raised to negative L over RT. Because the latent heat of evaporation is dependent on temperature, the exponents are substituted to this, where A, B, and C are constants, T is in degrees Celsius, and P is in hectopascals. This is also known as the Magnus approximation, a form of the Clausius-Clapeyron equation.
Now let us move on to the discussion of the application. The problem reads, a pharmaceutical tablet coating in a manufacturing plant is non-reactive at room temperature, 25 degrees, 31.71 hectopascals. In order for the coating to function properly, the surrounding vapor pressure must be 600 hectopascals. A. Find the temperature needed for the tablet coating to be manufactured. B. Additionally, the cooling stage requires the temperature to be negative 5 degrees Celsius. What must be the setting on the control panel to facilitate this? Let us first list down the provided information from the problem. We will use the equation derived earlier. While the constant A has a value of 17.625 and B has 243.04, P naught, or the pressure at room temperature, is 31.71 hectopascal. T naught, or the room temperature, is at 25 degrees Celsius. Additionally, P sub M is 600 hectopascals. And for question B, the cooling temperature, or T sub C, is negative 5 degrees Celsius. For question A, we need to first find the constant C and then find the temperature for manufacturing. Using the equation derived from the Magnus approximation, we plug in the values of A, B, T naught, and P naught as shown. And solving for C, we get 6.127. Now that we have the value for C, we can now obtain T sub M. After plugging in the values of P sub M, A, B, and C, we get this equation. And solving for T, we get T sub M is equal to 85.44. This means that the temperature to manufacture the tablet coating is 85.44 degrees Celsius. Moving on to question B, it is asking for P sub C, or the pressure needed for cooling the tablet. Using the same equation as before, the values A, B, and C, and T sub C are plugged into the equation. Solving it gives P sub C a value of 4.23 hectopascals, the pressure needed for cooling the tablet.
With this, the use of vapor pressure has many applications in the real world. One such example is its use in the pharmaceutical industry to coat tablets using heated air. Pharmaceutical companies create these tablets and medicines by controlling the vapor pressure to create ideal conditions for the tablets to be made. Due to this, controlling the vapor pressure in an area possible by using the Clapeyron equation, which includes factors such as temperature, latent heat of evaporation, and pressure to solve for the ideal vapor conditions needed for a tablet to be made. With this, many people are able to benefit from the use of tablets such as medicine. And so these are our reference that we use for our research. And thank you for watching.